the tension force. Now, by the word tension, it means that the force that occurs when you pull on a rope or a cable or string or rubber band, anything that creates tension, and the force that comes from pulling on that. So in the first picture, what you see then is a person's hand is applying a force. Well, whatever force that person is applying is transmitted, and we're going to say undiminished, through the rope to the object. So this tension that he's pulling with is actually the tension that the rope experiences. And of course, here, when I have equal and opposite tension on this rope, it is motionless. So the important thing you want to notice, though, is that the push or pull goes through cables or ropes or wires or whatever, and is transmitted just as though you were pushing or pulling it. Now, of course, you see here that this rope has to be tight. They call it taut. In other words, there's no slack in it, so that the object will then feel the full impact of the force. So, a massless rope will transmit tension undiminished from one end to the other. So again, this man is pulling down with this tension force. And as he pulls it across this pulley, this object is experiencing that force upward. And of course, we know a pulley is just a simple machine. In other words, this person could not lift this mass with his body alone. If this is something that's very, very massive, hundreds and thousands of pounds, he couldn't lift it. But a simple machine called a pulley enables him to do that, because we're going to see how a minimum amount of tension or force can do great work when we include a machine. Now, we use the word massless rope, but of course we know the rope is not massless, but for all of our calculations, we do not include the mass of the rope. Now, we assume that the pulley itself is frictionless so that we don't lose any of the force due to friction. But of course, class, in real life, this is not true. These are only ideal situations so we can solve these equations. In real life, this rope does have mass. In real life, there is some friction with the rope around the pulley. But for our purposes, we're going to ignore that. Now, last time I discussed equilibrium, and I gave you the equation. An object is in equilibrium when it has zero acceleration. That means all the forces in x equal zero. So that means then that all the forces in x, which could be mass times ax1 plus mass times ax2, so forth and so on, zero. Because the acceleration here is zero, or the object is moving at constant speed, which means it is zero. So therefore, we have what we call equilibrium. So again, how are we going to solve these problems? We're going to set up a reasoning, use a reasoning strategy where we're going to draw a free body diagram, determine our XY axis, and solve for the unknowns. So in your textbook, you have an example. If you have your book, I think even any book will have this example, even though it may not be on the same page. So I am on page, let's see which page I'm on. I am on page 103. This is example 11 in your textbook. So here we have, it says The picture shows a traction device used with a foot injury. The weight of the 2.2 kilogram object creates a tension force. So this object is creating force that is transmitted now around this pulley. Now the object, this is a picture of it, but over here we have our free body diagram, and the author just tilted it just because he wants you to see that even if I tilt it like this is still considered my x-axis, the one that's more closely to the horizontal, and this is my y-axis, the one that's most closely to the vertical axis. I could have easily drawn the same picture like this, but he wanted to just mimic what the orientation is for the foot. So let us then go to our whiteboard, and we're going to write down the equations. Now, in this case, nothing is moving. Nothing is moving means that we have equilibrium. Equilibrium on the x-axis and equilibrium on the y-axis. So on my x-axis, as you can see here, vector T2, right here, this is vector T2. I'm going to write T2 with this x and y component. Then I have tension T1, its x and y component. And then I have a force that's shown here that's parallel with his leg. And that force is on my x-axis and it's negative. So when I go to the, well, let's see, we might can solve it here. Let's see. So what sine means what? The y-axis. So this means that all my forces in y equal. So what are the forces in y? My first force in y is here. Okay, T1 sine 35 here. My other force in y is T2 sine 35. And of course, that's negative. So therefore, it's negative. And all of these, we said equilibrium must equal 0. Then I have all my forces in x, okay? All my forces in x. That must equal to 0. So on the x-axis, first I have T1 cosine 35 here. I also have T2 cosine 35 here. And I have this force, which is acting in the negative direction. So it's negative F, and that must equal to 0. So all I've done now is written the equations of equilibrium. Okay, so let us go now to the whiteboard and let us solve these equations. Okay, so all my forces we said in y, we had T1 sine 35 plus T2, which was negative. I'll just say negative. Hold on. Let me just say negative. Hold on. Erase. Minus T2 sine 35 equals 0. Then our other equation was on the x-axis. And there we said that we had T1 cosine 35. We had T2 cosine 35 minus F, and that is 0. Now, in the given, in the given, in the problem, it says that the forces arise in reaction to Newton's third law to the pulling force. And therefore it says that given the effect of the forces T1 and T2, let me show you the picture. Hope I don't lose this. Well, if you have your picture, if you remember the picture, the vectors showed us that the forces T1 and T2 would have to equal 0. In other words, the negative force right here I don't have the picture. I'm afraid to go back. I'm going to lose my equation. But from the picture and from the narrative, T1 is equal to T2. And usually when you have that case, you can just call it T, but we won't do that since the author didn't do that. So the magnitude of the tension forces are equal. They just act in different directions. So if that's the case, then let's just call this equation 1. Let's call this equation 2. So from equation 1, then, we can see that T1 sine 35 equals T2 sine 35. Okay, from 1. This is from 1. This is from equation 1. And of course, even here, even if we didn't have the picture, this would prove also from here. If sine 35 there and sine 35 here, that also proves that T1 is what? Equal to T2. So now we have an expression for T1, because we can say then that T1, we can have an expression for T1 or T2. The author chose T2. Oh no, he's called it T. Okay, good. I didn't look and read the problem ahead. So that's what I was saying also. Let me go back to here. If T1 equals T2, then we can replace that with just T. Doesn't have to have a subscript because they're equal. So that means then in my equation 2, I can replace T1 or T2 with just T. So let's just do that. T cosine 35 plus T cosine 35 equals F. In other words, I took F to the other side. So T cosine 35 plus T cosine 35, that would give me 2T cosine 35. And that gives me F. So now I've got to go back now to my picture. I hope I don't lose this. But if I lose this, let's remember this is where we are right here. 2T cosine 35. Let's go back to our picture. Okay, in our picture, as you can see, what is supplying the force? In other words, what is, remember we just read about the tension goes undiminished. It goes undiminished over this pulley. So therefore, this mass, or the weight of this mass, is what's going to supply this tension. So right here, I can find the weight, because the weight we said is mg. Okay, mg. So that that is the weight, that is the force that is supplying this. Okay, so hope my equation is still there. So let's go back to our whiteboard. Oh, good, it's still there. Okay, so that means then that for the tension here, I can replace that with mg. So I can say that the tension here is the weight, which is mg, and cosine of 35, and that gives me my force. So now I can solve for the force. All right, so this implies then that my force is going to be 2, m is, was it 2.4? 2.2 kilograms, G, 9.8 meters per second squared, and cosine of 35. Those all numbers. So now I can find the value of F. So in your calculators, let's solve for the value of F. Let's see what we get. First, we say cosine of 35, okay? Okay, we got cosine of 35, get that number first. Then we have times 2 times 2.2 and times 9.8. Okay, and we get 35.3. Okay, 35.3 newtons. So that's F. So now that we know what F is, we can go back to equation 2 and we can find out what T is. Okay, now we know what F is. So let me find some space. Hold on. Okay, so what did he ask us to find? Oh, that's all he asked us to find was the force. Okay, it says, we're supposed to find T1 too, right? Let me see what it says. Ignoring the weight of the, okay, because T1 will be half, T1 and T2 will be, it's just half of the weight here. Okay, that's all he wanted us to do. Find the force. Ignoring the weight of the foot, find the magnitude of the force. Okay, we found that. All right, let's look at one more real quickly. And I'm going to get this one started, and I want you to finish it. Let's see. Okay, the next problem, we have an equilibrium where we have T1 and T2 that are not equal, because this tension is due to a pulley up ahead, and this one is due to a man pulling. And then we also have the weight. So we have to be very, very careful now when we analyze these forces. Okay, now you notice also, class, that in these forces, we do not have contact force, the contact forces. In other words, this object is not in contact with the surface, and therefore there's no normal force. We make it everything frictionless, and therefore there are no frictional forces. But you still must analyze all the forces that are there. So we do have the weight, tension 2, and tension 1. So over here, you see that we have tension 1, and we have what? The y component and the x component. But look at this picture right here very, very carefully. You see, he gave us this angle. So we've already learned how to look at this carefully. You see, in this picture, the x component is T1 sine. Remember last time, and in both of these cases, the x component was always the cosine. So you don't get stuck on that. You have to be able to understand when it is the sine, because we say that the sine is opposite over hypotenuse. So in this picture, the cosine and sine have changed positions. Now over here with T2, since they gave us this angle, when we finish, when we complete this one, then we have the y and the x. Okay, you see this? All right, do you see what's going on right here with T2 and T? Okay, they gave us this one. I'm sorry. They gave us this angle. Now, what you could do, class, in each of these cases, really what you could do, if you want to have the standard form, you could just look at this angle. Because if this is 10, of course, this has to be 80. If this is 80, this has to be 10. But because of how the picture is drawn, we're going to solve it this way, so we won't confuse. So this is my angle. This is my vector here. So if I complete my right triangle, okay, my pencil's not writing. It's kind of small. If I complete my right triangle, then I have my component vectors. So let's see if you wrote them out on the equilibrium, okay? So you notice then here, my x component is T1 sine of 10. It's negative because it is on the left side of the origin, and then T2. So this is what he wants you to make sure you understand, that these now are, I guess you can say, not in the standard mode that we have them in. But we could have, because we could have called this 80 and this 10. In other words, class, go to your calculator real quickly. Put in sine of 10. Put in sine of 10. See what you get. Then put in cosine of 80. See what you get. And you'll notice that those are the exact same numbers. So we can always use the complement of that angle if we want to make sure that our x component was always sine. So now, what do we have on the x-axis? On the x-axis, all the forces in x need to be 0. So therefore, on the x-axis, we have negative T1 sine of 10 plus T2 sine of 80, and that is 0. Then all the forces in y. We have T1 cosine of 10, T2, oh, this is negative, hold on. Well, I'll have to say plus or negative. It's not coming off. So I have to say plus or negative. Okay, T2. My pencil color changed. Cosine of 80 minus the weight, and that gives me 0. Now, you may ask yourself, why is it that I have these two equations? I want to point out something you learned in algebra. When you have two unknowns, you have to have two equations. So we have equations here and equation here, 1 and 2, because T1 and T2 are my unknowns. Okay. All right. So now what happens? In the first equation here, we find the ratio of T1. Well, we're solving for T1 in terms of T2. So all we've done here, looking for T1, we took T2 to the other side. So they both were negative, but then I multiplied by a positive one, negative 1, so they're both positive. Or you cancel out the negative sign. In other words, right here, the extra step was, he said, negative T1 equals, over here, we had T2. To the other side, we would have negative T2. And then we would have sine of 80 over sine of 10. In other words, divide that by both sides. Then he said negative here, so they're both positive. So now I have T1 equals T2 times this ratio. Now these are actual numbers. Keep in mind, class, that this is just a number. So what I tell students to do, I say to keep from having it so confusing, what you can do in the meantime is you can just say T1 is equal to A, you can call it A, or anything you want to call it, times T2. Because this is just a number. And it's easy for you to work with a number than writing all this every time. So now I have an expression for T1. So now in equation 2, so equation 1, this is equation 2. In equation 2, everywhere I have T1, I can put in this. Now, I only did this to show you that this is just a number. But if I put it in here, okay, if I put in the ratio sine of 80 over sine of 10, that's my A here. And you can finish solving this problem out. And once you finish solving this problem out, you're going to find a value for T2. Okay, simplify it. When you simplify it as best you can, in fact, this is a good practice for algebra because now you only have one unknown, T2. That's your only unknown. You know W, which is the weight. You know this is a number here. You can solve for T2. Okay. Now, again, this is just a number. This is a number. This is a number. This is given. You can solve for T2. Once you solve for T2, you can go back into the original equation number 1, and you can solve for T1. So if I were you, I'd practice that because this is a good practice in algebra, as well as just manipulating the equations. Okay. Let's go to, okay. Now, if the object is not in equilibrium, in other words, the object is accelerating, okay, the velocity is not constant, then you have the same equation except for it does not equal 0. And the x-axis is ma sub x, and the y-axis, the force sub y, is ma sub y. So I'm sure you can follow this along. We have an example coming up Why is this stuff on one page still? We only have one problem where the object is actually in motion. So we'll solve that problem. I think that's the only, let me see. Yes, our last problem. Okay. So let's go back now to our homework and let's do some of the equilibrium problems first, and then we'll do one that's not in equilibrium. Let's go practice what we have first. Okay. Let us go, oh no, let us go to our assignment first. Let me go to stop share. Okay, I'm going to send this to you soon. After we finish this lecture, I'm going to send this to you. Okay, let me see. Yes. So consider the following forces. Which of the forces are considered non-fundamental? So non-fundamental, of course, are the forces that man creates. That would be friction, tension, and normal. Okay, let's look at one like number 3. 2 point masses M and M are separated by distance D. So in this problem, what they're saying is, here you have, let's see, why it's not writing? Hold on. Okay, here you have a mass, a point mass, okay, and this is M. And here we have D, and here we have M. So already we know that we're going to use the equation for gravitational force. So that force says that the force gravitational is big G M divided by D squared. So 2 point masses M and M are separated by a distance D. If the distance between the masses is increased to the 3D. So now this is my first case. In my second case, okay, the F sub G is going to be big G, little m, capital M, over, now I have 3D squared. Okay, in other words, now they have increased the distance between them by 3D. Now, the first thing I want you to know from this problem is this. Okay, if the distance between the masses is increased, how does the gravitational force between them change? And of course, you can see here, if the denominator gets larger, right? But what's happening to the numerator? It's remaining constant. So that means that the force has to go down by whatever factor this changes by. And clearly, this is big G, little m, upper M. 3 squared is 9. D squared is D squared. So clearly, the only difference in this one and the original one is what? The 9. That's the only difference. So therefore, the force will be 1/9 as great. In other words, this force compared to this force is 1/9 as much. Okay. Now, how about here? 2 point masses M and M are separated by distance D. If D remains fixed, but the masses are increased. So now I have in the first example, I have my force is G M over D squared. And the second case, this is the first case. In the second case, my force is 3M, and D remains fixed. So now I have 3 times 3 is 9. So I've got 9 G M M over D squared. So clearly the only thing that's changing is what? Is this 9. So now the force will be 9 times as great. And that's what we discussed when we went over this law. The force is proportional to the masses. That means ever how the mass changes, that's exactly how the force changes. But the force is indirectly proportional to the distance, the square of the distance between them. So if this gets larger, then of course the force gets smaller by that factor squared. That's all that's saying. Okay, let's find a problem to solve. Let me see. Okay, continue to look at these. These are concept questions, and they should be pretty easy for you to follow. All right. So what is the weight of a 2.5 kilogram bag of sand on the surface of the earth? And of course, that's easy because weight is simply M times G. That's easy. Now I want to use this problem to show you something else. What if I said, what is the weight of this is an example problem, and I gave you the mass, and I said that mass was 3 slugs. And in that case, you saw the weight to be 3 slugs, and of course, you don't use the 9.8. Of course, you use what? 32 feet per second squared, and your answer will be so many what? Pounds. What's that? 96 pounds. So make sure you look here to see what is the unit. If the unit is newtons, then of course you multiply this by 9.8 and you get your answer in newtons. If this is given in slugs, you multiply by 32 and the answer is in pounds. I'm going to use that problem to point that out because that's what's on the exam. I want you to see it before the exam. Okay. Okay. A projectile is a 20 kilogram projectile is fired at an angle of 20 degrees. What is the magnitude of the force exerted on the projectile when it is at the highest point in its trajectory? So, at the highest point, we know that force is mass times the acceleration at the highest point. Now, this problem is a good problem for you to use for concepts because we know that anything that moves along a projectile, it only has one acceleration, always, always, always. And that acceleration is due to gravity. So therefore, when you see this problem, even though they gave you an angle and all that, there's no a sub x, there's only a sub y. So mass times 9.8, and that's why this is my answer. Okay. All right, let's move down to another one. Okay. Now, what is the magnitude of the gravitational force? Okay, so what they're saying is you have student A with mass 79 0.5 kilograms. A distance D is 2.4 meters. And over here is my other mass, 58 kilograms. So of course, we're going to solve the equation. And the equation, of course, let me put some space there, hold on. Okay, so my equation is F sub G, which is big G, okay, M1, M2 divided by the distance between them squared. So I just plug that in. G is 6.67 times 10 to the minus 11. My units are Newton meter square over kilogram square times M1. M1 is 79.5 times M2. M2 is 58. Kilogram and kilogram is kilogram square. Okay. Then I say in the denominator, I have to put 2.4 square meter square. In other words, the number has to be squared, the unit has to be squared. But by me doing it this way, you can see that kilogram and kilogram square here will cancel, and meter square will cancel, and my answer is in newtons. So in my calculator, somebody do this. Multiply this number, not the exponent. Do not do the exponent. Multiply 6.67 times 79.5 times 58. And watch me what I'm going to tell you. Divide 2.4, divide 2.4. It's actually more accurate in this case for small numbers like this to divide it twice, because in some calculators, depending on the kind you have, when you hit that square button, it squares the whole thing. So I'm telling you the most correct way to do without an error, 6.67 times 79.5 times 58, divide 2.4, divide 2.4. And give me your answer in chat. Okay, let's see what you all are saying. Okay. Let's see why we have 79.5, 58, 2.4, 2.4. Okay, very good. All right, so the answers that I see look good. 5,339. Very good. So now my answer is 5,339 times 10 to the minus 11, because that's still there, and my newtons is still there. So now all I have to do is, of course, write this number in scientific notation. Okay, scientific notation means that this number gets smaller by 1, 2, 3. And I also, if I was writing this answer, I would say 5.34, because see, this number is a 9. I mean, this goes up to 1. So 5.34. This got smaller by 3. This must get larger by 3, which means I'm going to add a 3 to that. That'll give me a minus 8 newtons. So that's the answer that you should be getting. Okay, great. We got that answer. All right, very good. Any questions? Okay, let's find a different type of problem. Okay, so let's look at this problem. All right, a force P, here, P, pulls on a crate of mass M that is in contact with a rough surface. The first time you see the word contact, you know you have to have your normal force and you have to have your weight. The figure shows the magnitudes and directions of the forces that act on the crate in this situation. W represents the weight of the crate, F sub n represents the normal force on the crate, and F represents the frictional force. Okay, now, first thing we have to do to answer in these questions is analyze this problem. So let's analyze this problem. Okay, on my free body diagram, you notice that P has components. So on my free body diagram, if this is P, then I have to have P sub Y and P sub X. And my angle here is 60 degrees. So that tells me then that on the x-axis, okay, the forces on the x-axis are equal to, I have to have what? P times the cosine of 60. That's going to be positive minus 80 newtons. That's all I have on the x-axis. So what are the forces on the x-axis? They are 160 times the cosine of 60. Okay, and that has to equal, minus 80. So what is that? So if you do the cosine of 60, class, what do you get? Have you all learned some of these already now that we've been doing them several times? The cosine of 60 and the sine of 30 and all that? Well, by now you may have learned that the cosine of 60 is 0.5. So 0.5 times 160 is going to give you 80. So you got 80 newtons minus 80 newtons, and that gives you 0. So on the x-axis, all my forces add up to 0. Now, what are my forces on the y-axis? On the y-axis, I have, first of all, I have negative W because it's pointing down. And I have P, what's this right here? That is P times the sine, okay? I'm talking about this, P sub Y. P times the sine of 60. And we have what? The normal force. In other words, this component here is acting upward. That's my normal force, F sub n. But we know now that the normal force, remember we studied this before, the normal force here is equal to remember our picture where we had this acting downward and the normal force would be the sum of the forces. So this force is being added to that. Do you recall how we did that for the picture? So in other words, I need to know what is the magnitude of the normal force. So this component here, this component here is adding to my normal force. So what is that? What is P sine of theta? So now we have 160 times the sine of 60. Okay. So now my normal force, which is balanced off by this, would have to be what? Okay, in other words, if you recall from the picture, my normal force is going to be this force positive and this force negative. But the normal force itself is always a positive force. So we're going to have what for my normal force? If I put this on the other side, I'm going to have negative P sine of 60 plus the weight. So what do we get for that? Let's see. Plus we get what? We get what? 100, the weight, 196. 196 minus P sine of theta. Okay. All right, 57.5 something. 57.5 something. Okay, 57.5. Okay, oh, well, look, we've already answered this question. What is the magnitude of the normal force? We answered that question, but this question was first. The crate must be at rest. The crate must be moving with constant velocity. The crate must be moving with constant acceleration. The crate may be either at rest or moving with constant velocity. The crate may be either at rest or moving with constant acceleration. Now, this first equation that we solved right here gives us a clue because the sum of all the forces on the x-axis is 0. The second equation gave us a clue only because we know now, since we found out the value of the f of n, that this will also give us 0. But the important thing is, how are we going to determine which of these is true? Now, the crate must be at rest. The crate could be moving, because the only thing we need to know is that there is no acceleration. Remember, all the forces in x means that f of x is ma sub x, okay? And that gives us 0. So all we know from reading this intuitively is that on the x-axis is equal to 0, but it simply means that what? The object could be moving at a constant velocity. That also would mean that the acceleration is what? 0. It doesn't have to be 0. It could be moving at constant velocity. So that's why we're going to say no to A. Okay, must be moving. We already said it could be at rest too. So constant acceleration, no, because that would be what? That would be non-equilibrium. Okay, accelerating constantly is non-equilibrium. Okay, that means the velocity is changing. So then that's why we chose D. The crate may be either at rest or it could be moving with constant velocity, meaning what? The velocity stays constant, it's moving, but it's not accelerating. That's what that means. Okay, so we've answered that. Let's see. Okay, number 8. A block is set moving with an initial speed of 6 meters per second on a rough horizontal surface. If the force of the friction is 12 newtons, approximately how far does block travel before it stops. The first thing you see here when it says before it stops is that what? The acceleration, the object is changing its speed, okay? Whenever we have a change in speed, that means the object is what? Accelerating. A change in speed over what? Over time or over distance in this problem. So the object has to be accelerating. So we say that the force, okay, horizontal, so we say X, the force is ma sub x. Okay, and what is a sub x? Well, we're going to solve for a sub x because they gave us the initial speed, v initial, and that was 6 meters per second. Now, even though it's on a rough horizontal surface, in this problem, we're not concerned with the coefficient of friction, but later on we will be. Okay, and it gave us the final speed. They said it comes to rest, and it gave us the distance, x, which is 12 newtons. So I need for you to go to your calculators, go to your notes. First of all, find out what a sub x is, because now we have an equation, one of our kinematic equations we can use to solve for a sub x, then come back and solve for mass. For force. So do that. Go to your calculators and do that. Okay. So first of all, I want you to solve for a sub x. Once you solve for a sub x, put that in chat. And then, of course, it'll be easier to solve for the force. Please solve for a sub x. Let's see if anybody got it. Okay, always solving for first is a sub x. Did everyone go away? No one could find the value for a? No one recalls the equation to solve for a? Hello, hello, hello. Okay, if you remember, class, you had some equations, your kinematic equations, that said v final squared is v initial squared plus 2ax. So you're trying to find this A. You have V initial, you have V final, you have X. You can solve for A. So let me see who can do that. Nobody can solve it? Okay. Wow. Well, okay. Thank you, Nigel. Thank you. You have 6 squared, which is 36. And then you're going to divide it by 2. You're going to divide it by 12, and you get 1.5. Very good. Okay. And then 1.5, take that and multiply that by your mass of 8, and you'll get 12 meters. Okay. Let us go now to what we're looking for now. Okay, hold on. Let us go to, oh, okay. I solved this problem backwards. I was putting the 12 down for the X. It solves the same way because I was looking for the other unknown. Why did someone stop me? I'm looking for the other unknown. The 12 was given, and we're looking for this 12, but of course it worked out the same way. That's funny. Okay. I'm thinking that I must have lost some people because no one is responding. So let me see if I can find one more problem that will be on the exam.
Will 18 be on the exam? Or let's see.
Yeah, okay. I'm probably going to save the friction problems for the next part of the exam because everybody's getting quiet. When people get quiet and I'm not getting a response, that makes me think that maybe you're not following. So before I go any further, let me go to my equation quiz. Let me share. I don't have the equation quiz pulled up. Okay, I don't have the equation quiz pulled up. I don't have it printed in front of me. So let me just go back. Okay, you should have your equation quiz pulled up. And in your equation quiz, you have all the equations. Let's just stop at the well, I think I had a frictional force problem on the equation quiz. Okay, so let me just stop here. It's 2:36. Let me see what questions you have. What questions you have on anything I have covered so far. The only thing I need to go back and cover is non-equilibrium, which is sort of what I was solving just then. Okay, let me go back and solve that problem again because I was actually doing it incorrectly. Let me go back to that problem again. Let's see what error I was making. I don't want to leave an error out there. Okay, so in this problem right here, this problem I made an error. I wrote down, I thought that was the distance. Let me write it down again. Let's solve it again. Okay. So in this problem, we're given the mass, we're given the initial speed, 16 meters per second. We're given the final speed, and that was 0. And we're given the force. That's what I did wrong, incorrectly. So I'm going to correct that. And we're asked to find X. That's what I did. Okay, so clearly from here, from here, we can find the force, which is 12 newtons, is equal to MA. So that means that A then is 12 divided by M, and M is 8 kilograms. So we get A, and we get 1.5 meters per second square. Then we go to this equation. V final squared, which is 0, is V initial squared, which is 16 square meters square second square, minus 2A. A is negative, A is 1.5. A is 1.5 meter per second square, 2AX, and X where is my unknown. So when I solve this equation for X,
Is
that
it
means
16 or 6
uh,
for the V initial?
oh yes, that's incorrect. Thank you. Thank you very much. Let me change that. That make the whole thing different. Thank you. Okay. 6 meters per second square. And then when I solve for X, I've got 36 square, and I'm going to, this is not going to be what? Divided by 2, that will be 18 divided by 1.5, and that'll give me what? 12. So it's still 12, although we were solving for this 12. That's funny. Okay, so when we solve for X, then we're going to say 6 squared, which is 36, and I'm going to have meter square second square divided by, now, one thing you want to notice here, I'm going to point this out. The reason why this number is actually a negative number, because V final minus V initial, that means that if V final is smaller, the object has to be decelerating. And we know that decelerating always means that that number is negative. So make sure when you plug it in, you understand why we are dividing by a positive number and not a negative number, because X is distance, and distance can never be negative. So in this problem, when it says how far does it travel before it stops, it has to be a positive number. But how would it be positive? If I divide by this number would appear to be negative, but it's not, because we already know that when you throw an object up, the reason why it comes to a stop at the top is because the A is negative 9.8 meters per second square. Well, you say, well, what happened when it comes back down? When it comes back down here, the velocity is still negative because it's pointing in a negative direction. Okay? Here, the velocity is positive, 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 boom, it goes to 0. Here, the velocity is negative, 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 boom, hits the ground. So this velocity right here, this acceleration right here is a negative number. So when I put in negative 2, I put in negative 1.5 meters per, and I'm going to take second square to the numerator. So that means this one and this one will cancel. This will cancel one of those. Negative, negative becomes positive, and then I get my 12 meters. Okay. Okay, so we'll stop there. I'll let you digest that. If I were you, I'd work through these problems. We're going to first thing tomorrow, we will do a problem like this because we want to do one with frictional forces because the exam does have frictional forces on it. So number 18, yes, we have to go over, we're going to go over 18 and 19 and 21. We'll go over the rest of these tomorrow because we do have frictional forces on the exam. So we'll spend the first part of the exam doing that, and then we will review. So that means that on the exam, I'm not going to put tension. I'm going to take the problems with tension off, and we'll save tension to, no, I did go over tension, though, didn't I? Oh, no, never mind. I did go over tension. Okay, I'm going to send some problems tonight for you to work on with tension. So we'll review all that tomorrow. Okay, let me make sure. Yes, I'll give you a couple of good examples on tension tomorrow from the homework. In other words, I'm going to send them to you for you to work on, and then we'll be done. We actually have finished a chapter, so the exam can cover 1, 2, 3, and 4. Okay. All right. I will be available if you want to give me a text. I'm going to try to send you the problems as soon as I can find a few that will be applicable to what we've just done, and that we can work on those with relatively ease. Okay.
And the exam is Monday, right?
I'm going to put it over the weekend. So I'm going to try to post it. I still must learn how to post this exam. That's my my problem right now. And hopefully the software I was using is back up and working. Someone, when I inquired about it, told me that maybe it was a little glitch in Northwestern University. I was using their software. So maybe it's back up and running. I really hope so. And if it is, I might be able to put the exam in 2 parts. I thought about that too. This is what I thought. I thought about this. I said, well, I had already made out the exam for 1, 2, and 3. So I can just post that exam with a time frame for it. And then I can post the midterm with a time frame for it. And I can just include a few problems from 1, 2, and 3 on the midterm, along with the problems from chapter 4. So it'll be like maybe 40% chapters 1, 2, and 3, and then 60% chapter 4 on the midterm. But the exam that I've already made can be 1, 2, and 3. How does that sound to you all? Two exams, and I give you, say, from Friday, Saturday, Sunday, 2 different time frames to do it. How does that sound? That way you have a chance to get 2 different grades as opposed to 1 grade that may not be the best grade.
We could do that.
Any takers?
I'll be open to that.
Okay. All right. Well, I'll know more tomorrow. In fact, after I give you the homework, I'm going to look and see if that test generator is operating again. Okay. Look for some problems on tension. I'll just send a few for you to work on those.
All righty.
Okay.
Thank you.
All right. Y'all can sign out, and I'll see you on Thursday.